Welcome to this video on the question, what is capacitance? And here we're speaking specifically about electrical capacitance. Now you may have heard the term capacitance before, or the term capacitor, or maybe even the term flux capacitor from the Back to the Future series, and unfortunately that's not a real thing. Capacitors, however, are ubiquitous in all of the electronics and many of the devices we use. But not only that, capacitors actually occur naturally, because they're really just talking about relationships between regions of places. And so if you look over here from the awesome simulations from the FET.Colorado website, we see here we have a very basic capacitor. And this very basic capacitor is just literally two conducting plates separated by a gap of insulation. Here the insulation is just a vacuum or air. Now, you see that this configuration is that it's attached to a battery, and we're going to get into that in a few minutes. So let's just talk about what the heck this term capacitance actually means. Well, you probably can think of a very common root word, which is capacity, and oftentimes when you think of that term, you think of the ability of a space or a vessel or something to hold some amount of things or people. So in other words, maybe there's a certain 15-person capacity for the elevator, or a 2,500 kilogram capacity for the elevator, or perhaps the maximum capacity for a particular floor of a building is a certain amount, or a bookshelf you purchase has a capacity for X number of pounds on a particular shelf. So the term capacity often implies a limit of some kind, or a limitation, but it also describes a total amount of something that can be held per region of space, or per separation. So there's this idea of amount of something, a quantity per some space or some region or some classification. So when we think of the term capacitance in terms of electricity, we're going to use the symbol uppercase C to represent capacitance, and we're going to define it as the amount of charge that can be stored in a particular region per volt of potential difference. Now, it's a little bit deceptive, because if we're thinking of this idea of space and we're thinking of this idea of potential difference, we really should put this delta in front here, because now it does describe a location. It says relative to some other place, this other place can hold X amount of charge. Now what I mean by that, if we look at this example, is relative to this bottom plate, the top plate can hold X amount of charge per potential difference between the plates. Now let's go back and let's think about the process that we talked about in previous videos of how to set up an electric field. The first thing that we needed was work. Work had to be done by some external force in order to separate charge that would ordinarily want to be together. If we separate charge, that leads to a potential difference between the two locations. And if there's a potential difference, an electric field is established. And then that field, of course, can exert force to do different things. Now there's a little bit of a conundrum here, because in order to separate charge, in order to do work, we need to have a potential difference to begin with. But the act of separating charge also creates potential difference. So what we oftentimes would say here is that this is kind of a cyclical process over here, whereby the act of doing work requires a starting potential difference that will then separate more charge. It's all about locations. So if we look at this scenario over here, the battery itself, let's call it 1.5 volts. This battery is a potential difference, right? Or has a potential difference from side to side. So here we would say there's 1.5 volts of potential, and here at the bottom we would say there's 0 volts of potential. Now don't be confused by this dial over here. This is just showing us the maximum voltage we can have either way, and we can switch the polarity of the battery. I have to have this potential difference, and the battery does work. So what I'm going to do here is I'm going to go ahead and write in each component of this little circuit that does different steps in this process. So the work is done by the battery. And something important to note is that the battery is one of the sources in the circuit of potential difference. So we have the high potential and the low potential. The positive is the high potential, the negative is the low potential by convention. And that potential difference allows us to separate charge between the plates. So charge is pulled off of one of the plates. We can see here it's pulled off of the top plate and dumped onto the bottom plate. So in essence, what's happened is the battery is doing the work needed to separate the charge. Now, as I slide the charge dial over here, you can see that more or less charge is being separated. So over here we might have X number of charges being separated. If I increase the potential, we see that there's more charge separated. So going back to this definition here, we see that this is a ratio of sorts. But as we adjust the voltage of the battery and the charge amount adjusts, and I'll go ahead here and I turn on the meter for the charge, I see that the charge is actually changing as I change the voltage. If voltage goes up, charge goes up, but the capacitance is unaffected. So we have to be very careful here. This is a definition, but there is no relationship between the voltage or the potential difference and the capacitance, because when we change voltage, charge changes too. And we see that here in this little cyclical process. I'm establishing a potential difference across the plates. So this is the other location where potential difference happens. I establish a potential difference across the plates by separating charge or putting a quantity of charge on one of the plates. And so this process is dependent upon itself. So you see here that the capacitance is not dependent on the amount of charge independently, nor the potential difference across the plates. It is set by something else that we're going to take a look at in the next video. Perhaps a better way to look at it would be to graph the amount of charge that you could have on this particular capacitor plate versus the potential difference across the plates. And if I were going to actually take numbers, so perhaps I'd actually need to get my voltmeter out here and actually measure the data for voltage and charge for a variety of different combinations, what I find is that I have a direct proportion. And if I write this out, I see that this is a linear graph, y equals mx. And I see that y can be substituted with q, that x can be substituted with delta v, and then m, it becomes clear, is the ratio that fixes these two values together in this particular scenario, and that's capacitance. So the amount of charge that a plate can hold depends upon the potential difference that is attached across the plates and the capacity of the plates to hold charge. So you can see here this term capacitance is inherently occupied by the plates themselves. Their ability to hold charge will determine how much charge they can handle per volt. I always think of this idea as a fraction, simplifying a fraction. 100 coulombs of charge, for instance, might be possible across 10 volts. Or perhaps that's the same thing as saying, if I have 10 coulombs of charge, I only need 1 volt to do that for this particular capacitor. And the capacitance of this capacitor, if I was using these values, would be just 10 farads. So if I said I have a 10 farad capacitor, that means it can hold any combination. Well, I say that with reservation, but any combination for now of charge per volt. So if I want to hold 10 coulombs of charge, I only need 1 volt of potential difference across. If I want to hold 100 coulombs of charge, I only need 10 volts of potential across. So you can see here that this idea of capacitance is the ability of a region to hold a certain amount of charge per potential difference or per volt between the two regions. The battery establishes the potential difference so it could do work to separate charge from the plates or between the plates, and thereby creates a potential difference across the plates. And the potential difference across the plates matches the potential of the battery when the process is said and done, constructing an electric field, as we will see here if we turn it on, between the plates. When there is no potential difference, there is no charge, even though there still is capacitance, or it has an inherent capacity, but there's no field. So in the next video, what we're going to do is take a look at what actually determines the capacitance of the capacitor, if the definition of capacitance is the amount of charge per volt.